So we are going to start with a link. We are going to find a diagram for this link. So let's call D a projection diagram. For L. And once you have this, what we are going to do is we're going to define this bigraded chain complex, C of D. This is going to be a bigraded chain complex that comes from this diagram. And then we are going to take a homology of this. So H star star of D is going to be sum of Hij of Z. So this is going to be kernel mod the image, and we are going to look at this homology over here, and we are going to call this Kovanov homology. Okay. So in order to do that, I have to tell you how do I define this, and I have to tell you what are the Dij maps so that you can take homology to compute the Kovanov homology. So this is what we are going to do next. And the key thing that you should keep in mind is the following things. So the first thing is that throughout this process, what you should make sure is that there were many choices that were involved. So especially here. So given a link, there are many ways to get this diagram. But as we've seen the first day, any of these diagrams are related by Reiter-Meister moves. So what you need to do is that this resulting thing does not depend on the choice of that diagram. So the first thing that you need to make sure is that if D and D prime are related by Reiter-Meister 1 and 2 and 3 moves, you want to show that H star star of D is isomorphic to star of D prime. So this is one thing that you need to make sure to get a not invariant. And second thing that we've been talking about was this actually categorifies Jones polynomial. So the second thing that we want to get is that from this not invariant over here, is it possible to recover the Jones polynomial that we've been talking about? And in order to get that, we'll be taking this graded Euler characteristic, CFD. And this is going to give us this unnormalized Jones polynomial of your knot. Okay. So this is another thing that you should keep in mind of. So let's start with a diagram. So I would like to recall how we got the Jones polynomial. So from D, we have this hypercube, and each vertex of the hypercube, you can think about it as an element of 0, 1 to the power of number of crossings in the diagram. Okay. For example, when we're looking at this half link, also remember when you have crossing like this, there were two ways to resolve it, either from north and south and west and east. North and south, we labeled with 0, so west and east we labeled with 1. So for this, we have two crossings. So we'll be taking a state in 0, 1 to the power of 2. So there are 4 vertices. So you have 0, 0, 0, 1, 1, 0, and 0, 0, 1, 1. They're connected like this. And 0, 0 corresponds to resolving both of them with north and south. So the picture looks like this. And 0, 1 should look like this. And 1, 0 should look like this. And 1, 1 should look like this. Okay. The first thing that we did was we counted how many circles we had. So we had 2 circles here. So for this, we had Q plus Q inverse squared. And also for these circles, there are 2 of them, so we have Q plus Q inverse squared. There's only 1, so we have Q plus Q inverse. For this, we have Q plus Q inverse. Okay. And next, what did we do? We said I would like to multiply minus Q to this factor. And with respect to the number of 1s that I have on alpha. So in this alpha, I don't have any 1s, so I don't multiply any minus Q. But for this, I have 1, 1, so I will be multiplying minus Q dd1. The same thing for here. I multiply minus Q. For this, I have 2 1s, I'll be multiplying minus Q squared. Okay. So the Kaufman bracket for this diagram was summation of all of these 4 factors. You take a summation of alpha, which is contained in 0, 1 to the number of crossings, and you do minus Q to the number of 1s in alpha, multiplied by Q plus Q inverse of number of circles in this state. So let's call that gamma alpha. Okay. So this is the formula. So instead of writing this over and over again, I'll call this R alpha. And number of circles in gamma alpha, I'll call this K alpha. Okay. So using this, the unnormalized Jones polynomial we can write it as J hat D of minus 1 of n minus times Q of minus 2 n minus plus n plus of the Kaufman bracket. So remember, n plus is number of positive crossings, and n minus is number of negative crossings for the link. So it's 1 to the n minus times Q dd minus plus n plus times summation of alpha of Q dd R alpha times Q plus Q inverse of K alpha. And I'm going to put this fellow inside. So this turns into summation of alpha of minus 1 TD and minus plus R alpha times Q to the minus 2n minus plus n plus R alpha times Q plus Q inverse K alpha. So this is how you get the Jones polynomial in general. This is how you systematically compute the Jones polynomial. From D, I'll be choosing a state alpha. And from there, I'll be defining V alpha. V alpha is defined in this way. So I'll be taking tensor product of V K alpha times. Remember, K alpha is number of circles in the state. So for this it will be 2, for that it will be 1, for this it will be 2. And I'll be doing a grading shift, minus 2 minus, 2 minus, plus m plus R alpha. So these were number of crossings. M plus was positive, this was negative, and R alpha was number of ones that you see on the alpha. I'll be doing V tensor V. So I'll just write it as V tensor V. Because I have 2 circles, I'll be doing a grading shift. For us, there are only, wait, should be just positive 2, sorry. So I'll be doing minus 4. And R alpha, there are no ones on the circle, so I'll be just doing minus 4 as a shift for this state over here. A logical grading is given by R alpha minus M minus. So it's number of ones that you see in alpha, and you're going to subtract by. So for this, the homological grading is going to be 0 minus 2. So this will be minus 2, homological grading. Homological grading from left to right. So the point is, when you start here, when you move to the right ones, homological grading goes up by 1. And from here to right, goes up by 1. So I have minus 2, minus 1, and 0. So this means that if I want to define a differential, I need to define a map from here to here, and from here to here. So that's what I'm going to do next. But before we get there, I'd like to convince you that if I take the Euler characteristic of this complex, this will be spitting out this Jones polynomial over here. This is what I want to talk about next. So this homology was defined in 2000 by Kufanov, and so it took about 10 years to see if this is true. So this is a theorem of Kornheimer and Morovka. Which says the following thing. So the point is that this is a knot invariant. So if you have a knot, and if your knot is the unknot, if you compute this invariant that we talked about, they should spit out the same thing. Okay, so when I write this KH, there's a whole bigraded chain complex where you take the differential, so kernel mod the image, and the information that comes from the kernel mod image, we are going to call this KH. And the key thing was that so this follows from the fact that Kufanov homology is a knot invariant, and the remarkable thing is that in fact this is if and only if. So if you know how to compute Kufanov homology of your knot, it tells you exactly if it's the unknot or not. Invariant. One notable thing about this knot over here is that even though there are no other knots that have the same Kufanov homology as this knot over here, but if you compute the Jones polynomial of this knot, and the Jones polynomial of this knot over here, they give you the same information. They have the exact same polynomial, but the point is that when you actually, so this is the same, but as I mentioned before, Kavanagh homology detects this T25 torus knot. So they are the same, but when you compute the Kavanagh homology of this knot versus Kavanagh homology of this knot over here, they are not equal. So somehow the effort of going through all these algebra and getting this new invariant, in fact, tells you slightly more. In fact, a lot more information than the Jones polynomial itself. 3, you can think of it embedding of a circle, which is we've been calling it a knot. So let's say I have a knot inside R3 times 0, and let's say also I have a knot in R3 times the interval. Okay. Suppose inside this fourth dimension, let's say there is a cobordism between them. In other words, let's say there is a surface that is co-bounded by these two circles. So cobordism can look something like this. So you could have some holes. Okay, so you have this interesting surface that is embedded inside this R3 times interval, where the very left, let's say I have K, and let's say in the very right, let's say I have K prime. Okay. So what happens with this Kavanagh homology is that this surface, let's call this sigma. This gives you a map between Kavanagh homology of K and Kavanagh homology of K prime. So which you can't really say anything when you're just talking about polynomial. We can't really talk about maps between polynomials, but now we have vector spaces, so it makes sense to talk about maps between vector spaces, but the information comes from cobordisms between them. So once you have this, then there is a linear map. Let's call it Kavanagh of sigma from Kavanagh of K to Kavanagh of K prime. Okay. So now this becomes an interesting thing. Let's say, so now before we were just interested in taking two knots and see if those two knots are the same or not. But let's say I want to bump up a dimension 1 higher. Now let's say I want to compare two-dimensional surfaces and see if those surfaces are same or not inside this fourth dimension. So I give you this red surface, and later you come to me and you present a different surface. Sigma prime, and we want to compare if the sigma and sigma prime is the same or not. Okay? So what we have to do is you compute this map and you compute sigma prime of this map and see if these two maps are the same or not. If those maps are different, we can conclude these surfaces are different. So we are going one-dimensional higher than what we were doing before. Looking at surface from this way. I won't finish drawing it, but there is two different ways to draw a surface for the same knot. So those two surfaces, let's call this, let's call this yellow surface sigma. Let's call this red surface sigma prime. And those two were surfaces that live inside three-dimensional space. So inside this three-dimensional space, it was easy to see if those two are different in 3 dimensions. The fact that these two surfaces are different in the 4th dimension was a question that remained for a long time, but it was recently solved by using Kavanagh homology. And I want to end my lectures here. Thank you. It wasn't clear that such surfaces existed in the 4th dimension, but this was the first example that was found recently, and it uses this Kavanagh homology map.